Okay, thank you. So I'm Benoit Lamy Chappuis, and for the last 2 years or so, I've been developing a well model, like for the purpose of modeling the production of supercritical resources. So the main motivation initially was to try to simulate the IDDP2 well and the surrounding formation, including magmatic heat source. And I'm going to restrict a little bit this presentation to like this particular question. Like we want to understand the starting behavior of the well, because as you may know, this well was not was not self-flowing. So we wanted to know why and if there was any way to trigger the starting of the well. And to do so, we realized first we needed to use accurate fluid thermodynamics, so relevant and accurate at those pressure and temperature conditions. And in particular, we wanted to include NaCl salt into our equation of state, because there's a chance that there might be scaling due to air light in this well. And another thing that we wanted to add to our model was the possibility to account for the displacement of an air-water interface. So that is to say, we don't necessarily want the well to be always fully saturated with water, because if it's not flowing, it means that there is some air in the well and the water column does not reach the surface. So I'm going to show you a little bit the concept, general concept of this model. So here on the left, you have like an extensive formation domain, which is 12 by 12 by 9 kilometers. And in the center of it, this red straight feature would be the well. And so this is already a little bit of a spoiler from what's going to come after. But what you can see here is like a permeability structure. So with a low permeability cap rock, a central zone which is slightly higher permeability, because it might be quite fractured. And then a very ductile basement, very impermeable, because there is a high so yes, so there is this air-water interface that's going to act as a moving boundary condition for pressure, basically. But so now to represent like those segments, so earlier in the presentation from Alina, you saw like the well was just located in nodes. So here you have a mesh made of tetrahedral elements, and at the edges of those elements, you have nodes, and basically those segments of the well, they're going to connect two nodes of this mesh. And so in those elements, you have the primary variables of the well. So you're going to have like at the top of the segment the pressure and the velocity of the fluid. And in the center of the segment, we have like the specific enthalpy of the fluid, the salt mass fraction of the fluid, and the temperature. And then at the bottom of the segment, so located in a node, we will have the source terms that are calculated the same way as Alina is doing it with the Pisman model. And you have more elements up there, and all of those segments will be connected to each other. So in a straight line, because I made a particular mesh here. So now we want to solve like which equation we want to solve on those segments. We want to solve like mass conservation, momentum conservation, also known as pressure equation, energy conservation, and salt mass conservation. So basically here, mass conservation is simply like the divergence of the flux and a source term stemming from inflow and outflow or exchange of the formation. Momentum conservation, so it's just describing the change in pressure over the length of the well. So X would be just like an increment in space in the direction of the well, which is just a 1D segment. So this change in pressure is just a function of gravity, so the weight of the water, and a friction term that depends on the velocity and the friction factor. And then inertial terms. And the energy conservation is just stating that the transport, there is the divergence of the flux of the internal energy and kinetic energy that balancing out with the change in gravitational potential energy, and then heat loss term that is like conductive heat loss with between the well and the formation, and its source term again stemming from exchange with the formation. And then salt mass conservation also stems from the transport of, so this is the total concentration of salt in the segment, changing over time in function of like the transport of salt within the fluid. So this is the salt mass fraction of the fluid. And another source term again, because there is exchange with the formation. So I'm going to show you very quickly like the discretization. So it's, like I said, 1D and implicit and upwind. So I'll show you one example for continuity for mass conservation. So here we have the residual of mass conservation for segment N, this segment. And this residual is equal to, so the mass of fluid contained in the segment minus the mass of fluid contained in the segment in the previous time step. So the mass of fluid is simply the multiplication of the length of the segment times the cross-sectional area of the segment, which can be modified with Li precipitation. So that's why we have a cross-sectional area like effective times the density. And so this change of mass over time needs to be balanced by the, so here you will have the outflux of mass from the segment. So it's simply like this velocity times the cross-sectional area times the density contained in this of this segment. And the inflow from below, so you have like the velocity coming from the segment just below times the cross-sectional area of this segment times the segment below, and times the density of the fluid contained in the segment below, plus potentially a source term. So all of those things normally needs to come up to 0 if we have perfect mass conservation in this segment. So we solve the whole well in one go in coupled manner using the Newton-Raphson method. So here you have like at the initial time, you have the solution vector. So this will contain pressure, velocity, specific enthalpy, and salt mass fraction ordered like this, so from segment 1, then 2, 3, 4 until the bottom of the well. And so this solution vector needs to be, we have an initial guess, maybe coming from the solution of the previous time step. And when we have, knowing this initial guess of the solution, we can calculate all of the residuals. So I showed you one example for the mass conservation residual. And so we have here on this side like the residual vector, and we construct the Jacobian matrix of the well. So that's basically the derivative of those residuals with respect to all of the primary variables of all the segments. So for instance, here that would be the derivative of all the residuals of segment 1 with respect to the primary variables located in segment 1, and etc. And so when we like basically make this operation, we find a little increment in the solution that's going to take us closer to finding the 0 of all the residual here. And so here I expand like this basically term here is actually a bigger matrix. So that contains the residual of for momentum, mass conservation, energy conservation, and salt mass conservation with respect to all of the variables, P, velocity, specific enthalpy, and salt mass fraction. And so we keep iterating like this, making this operation until we either find that the residual is close enough to 0, or that the relative residuals, so that would be, for instance, for momentum, that would be the error in pressure divided by the pressure of the segment, is also below a certain threshold. So for instance, if the pressure in the segment is 1 bar and we have 0.1 bar residual, then that would be that would not be good enough. But if we have like 10 power minus 4 bar, then that would be good enough. And so this is like the flow chart of the global well and reservoir model. So we solve reservoir pressure with the CVFM scheme presented by Alina, and then we solve the well. So this means computing the well reservoir exchange terms with the Pisman formula, and then computing the residuals and the Jacobian, solving this system, and then at every iteration updating the thermodynamic properties of the segments, and also like updating the location of the air-water interface. So basically, this is simply mass balance. If you know the mass of fluid contained in the well, then you can figure out where this interface is located because you know the density of the fluid in every segment. And so we have here, it's basically a loop to solve a Newton-Raphson loop to solve the well. And then we have a partially implicit coupling between the reservoir and the well. So we just solve the well, which means that now we have different pressures. So we're gonna have different source terms between the well and the reservoir, so which means we're gonna have a different reservoir pressure solution. And so we just iterate between the reservoir pressure and the well pressure until basically the reservoir pressure is not changing anymore. So that's when we say that both the well solution and the reservoir pressure solution have converged, and then we can move on with the transport scheme for the reservoir, etc. So just again to reiterate on the small test we made to check if like the implementation of the source terms was right in our model. And because that was like a very critical aspect of the model. So we did this quarter 5-spot simulation with like a 1 by 1 kilometer square with an injector on one side and a producer on the other side. And under very specific conditions, so again, 250 bars, 140 degree, we compared our results with the results coming from Eclipse simulations. And so we have the producer at 280, the injector at 280 bar and producer at 220 bars. And we have here the pressure profile between the two wells. So this is just the pressure along the diagonal here. And you can see that the pressure, so from our model, so that's the straight lines, that's the lines, and the result from Eclipse, like the symbols, seems to match pretty well, especially our model matched very well the result from Eclipse at 10-meter resolution. And this translates into like flow rates in the well of 3,746 tons per day with Eclipse and 3,745 tons per day with our model. So that's a pretty good match. So now we move on to air pressurization and how we can use that to start the well. So first, very, very simple concept. You might have in the formation like density varying with depth, and in particular, you might have density maybe decreasing with depth, like this. And so the pressure within your formation will follow this sort of trend with a break in the slope of the pressure when you have a change in density. So here I just show a step, but in reality, it will be more gradual. And so if you have thermal equilibrium between the well and the formation and you apply air pressure, you're going to have basically air. If you apply this air pressure, you're going to fill the well with air all the way down here. And then you're just going to follow the same pressure profile. And once this is established, what you can do is to try to drop the pressure. So you will raise the water column inside the well, and you're going to start to draw maybe lower density fluid from here up here. So you're going to have like this this difference in density. So this red line would be the density in the well, and the black would be in the formation. So what you achieved here is that you have a different pressure profile in the well and in the formation. And so you have a pressure drawdown. And so once you have extinguished all of the air pressure, you hope that maybe you will have sufficient pressure drawdown so that the well will just like self-sufficiently, flow. So the limiting factors for this would be like thermal reequilibration, because if you're not doing it fast enough, then this fluid will start to cool down and density will re-increase because it will cool by thermal like temperature diffusion with the formation. And another limiting factor will be the density profile. So the biggest density change you have with depth, the easier it's going to be to basically create this a big pressure drawdown, because you have a bigger density difference between the well and the formation. Another thing that might help is that you might have actually boiling in the well. If it's sufficiently hot and you drop the air pressure down to sufficiently low pressure, then the top of the water column in the well here might actually boil and suddenly drop in density dramatically. And so what you might want to do, depending on the particular configuration, is to have maybe higher air pressure so that you can draw fluids from a lower zone, and you have more like basically more time to create this pressure drawdown. And so this is something I did, so with something very generic. So I took formations 5 kilometer deep with different bottom heat flux. So you can see here 200, 150, 100 milliwatt per meter square. And so this, then I just generated some homogeneous geothermal gradients through the formation with like increasing like a geothermal gradient like this. And so when you have this sort of temperature profiles, you also generate for a pure water case like this sort of pressure profiles and those density profiles. You can see in the very hot case, particularly, you have like at some point at 4 kilometers, a sharp drop in density, and this actually correspond to the supercritical resource. It's like once you get into the supercritical zone, you have this big drop in density. And so here I plotted like the air pressure that you would need initially to start the well. So you need this amount of air pressure in bar to start the well, depending on basically the temperature of the formation. So, and you can see that the hotter the formation, the easiest it is to start the well. So in the 200 milliwatt per meter square case, you only need maybe 20 bar air pressure. So the well is already almost self-flowing in that case. A slight perturbation in the pressure in the well, and as soon as you're going to have like some fluid flowing up from this area, it's going to basically create a massive pressure drawdown. And so this is not really dependent on the permeability, but I mean, in the range of 10 power minus 14 minus 15 meters square, it's this curve is more or less the same. So now that I talked about this very generic, I'm going to simulations. I'm going to talk more in detail about the IDTP2. So I showed you earlier, like we have this formation with this particular permeability structure. And this was basically, we determined this permeability structure such that we would manage to reproduce as well as possible the temperature and pressure that were measured or inferred with geophysical method around IDTP2. So basically, those black dots represent our best guess for the temperature near IDTP2 and the best guess for pressure. And if we have this particular permeability structure, and if we place a magma chamber, again, we placed it based on geophysical data that we assume that it would be sitting just below the well at around, with the top of the intrusion at about 5 kilometers, and an intrusion that would be 2 to 3 kilometers deep and around 1 kilometer or 1.5 kilometer wide. So if we do this and we let the system, we place the intrusion and then we let the system evolve naturally, we can reproduce more or less the state of the natural state of the system near IDP2. So of course there's like big error bars down here, but I'm not showing them. Like there is big uncertainty of the temperature, but we know that roughly at the bottom of the well, at 4.5 kilometers, we're going to be eating like a supercritical resource at around 500 degrees. So we have this state of the hydrothermal system, and now we want to characterize a little bit better the well, and in particular, we want to know like what's the property of those feed zones here. So first, why do we think there are 3 feed zones? And that's because there was a cold water injection test that was performed in IDP2. And so basically we inject cold water at around 30 degrees and at a rate of about 45 kilograms per second. And these black dots again represent the temperature profile measured in the well during this cold water injection. And like here in particular, you see a big bend in the temperature profile. This means that there is like big outflow of this cold water in this area. And so suddenly you have a much smaller advection of cold water down in this part of the well. And so there is more like there is a bigger component of heating due to diffusion from between the reservoir and the well. And so you have this sort of like temperature profile. Now here you have such high flow rate that you basically have isothermal flow at around 30 degrees. And then you have another slight drop at the end. But basically, if we use this set of permeabilities for those 3 completions, so the 3 completions, there is one at 2,000 something meter. Yeah, it's barely visible, but there's a small variation in the curve of the temperature here. And if we put this permeability here and this permeability at 3.4 kilometers and another one slightly low permeability at the very bottom, so here, we can reproduce again quite well the temperature and the pressure profiles during the test. So this is basically a quite good like calibration of the model. And I think what you can remember from this is that you have like a very dominant feed zone just at 3.4 kilometers. Then what happened with this well is that following drilling, there was like 2 years injection of cold water. And so I first modeled this part, so using the permeabilities of the feed zone determined earlier. I modeled the injection of cold water for 2 years. And you can see the results, the temperature profile inside the reservoir. So you have cooled down significantly the reservoir in those 3 feed zones. So it's just like this is the profile along the well, but in reality, in the formation, it's just like those small cold spots that you created by injecting the cold water. So what would that mean for well starting? So I'm going back to those curves, and maybe you remember that like this red curve like meant that, or for the density meant that it would be very, very easy to start the well. And now this cool black line is the density profile in IDP2 before cold water injection. And you can see that there are also like massive changes in density with depth, with very low density being encountered at the bottom feed zone. So this should be very favorable to start the well in theory. But what happened after injecting cold water for 2 years is that you created like very dense cold zones near the feed zones. And so because of that, it's now impossible to start the well, especially because this feed zone at 3.4 kilometers, the coldest one, is going to shortcut everything. And so when you're going to start to depressurize the well, you put air pressure and then you remove air pressure, you're just going to draw very cold and heavy fluids in the well, and it's not going to be possible to start the well. So I just try to look at, okay, what if we didn't inject cold water, then or if we wait for long enough until the formation warm back up, will it then be possible to start the well? And so this is like the result. So this is very short term. So this is after 3 weeks. So I applied some air pressure and then depressurize it, and I see that it's possible to start the well. So here there's many graphs. So in everything in red would be property profiles in the well, and in blue would be in the reservoir. And then you have the pressure, temperature, specific enthalpy, density, velocity, liquid saturation, and the exchange between the well and the formation. So you can see that in the hot case, so the temperature profile now is back to like the undisturbed temperature profile without injecting cold water for 2 years. So it's here, and you managed to basically by starting the well, you managed to get like a very different pressure profile in the well than in the formation, because you managed to draw hot fluids from the feed zones, and those hot fluids, as they rise to lower pressures, they will be very low density, and so overall the whole well is gonna be operating at very low densities. So this is the density profile in the well now. And so you have like those 3 feed zones. Here you can see a small bump in the pressure because you are drawing fluids and depressurizing the formation near the feed zones. You have like the temperature in the well. So here this small drop is caused by the depressurization between the reservoir and the well. And then you have a more or less isothermal and isenthalpic flow up to the next completion, where you have another inflow of fluid that is slightly colder. So you have a drop in enthalpy. And then up to the last feed zone, where you have another small drop in enthalpy, but no drop in temperature. And so basically here again, what you see is that the middle feed zone is really dominant with around 35 kilograms per second, while from the very bottom, where there is the most desirable resource, you don't really have any exchange because of the low permeability. And then you have this interfering like bit damaged zone in the well that also doesn't really help, because it's also drawing some colder fluids into the well. And at the very bottom of the well, you can see that you start to precipitate a little bit of salt under those conditions, but then above, you don't really have any salt precipitation, mainly because you still maintain, it's cold enough to maintain a liquid phase in the well, which carries most of the salt with it. So now I was wondering, like, what if we just keep the bottom filters? What if we could like seal the damage zone here and this feed zone, which is not super desirable, and only try to produce from the very bottom. And so in that case, you can actually start the well, because this bottom feed zone is there's some fluids, some high density fluid are going to trickle up and be warmed up against the reservoir, and basically eventually manage to again create a very low density fluid through the whole well. And so in that case, the only problem is that you have very, very low exchange, because again, this feed zone is very low permeability. So you would not really achieve any economically viable production rates if you only had the bottom feed zones. That's in the cold case. And if you wait for long enough until the formation is warmed up, then it's actually not much better. You do have, so here you see the enthalpy produced is very, very low. The temperature also very, very low. Again, it's because you have very cold fluids produced. But if you wait for the formation to warm up, then okay, you have like high enthalpy for more than 3 megajoules flowing through the well. But again, it's such small flow rates that it's not interesting. So I just then went on to ask myself, like, what if we could enhance this bottom feed zone? What if we could multiply the permeability by 100, basically? And so if we do that, then, so in the cold case again, we can start the well, because we could start it anyway before. So now it's even easier to start it. And we have like appreciable flow rates of more than 40 kilograms per second at around 3 megajoule, at slightly low density, so around 50 kilogram per meter cube. And so even, yeah, okay. And then we have again a slight amount, a little bit of halite forming, but not so much, because we actually injected cold water, so, and fresh water. So actually around the well in this feed zone, we don't have much salinity yet. So what if we just jump in the future again and we look at what's going to happen once the formation comes back to hot and draws back some saline fluids into the well? And now this is the result. So if we have a hot formation, and as you can see here, you have like a dramatic precipitation of halite. So because like, even though I think the produced fluid from the bottom feed zone only contain around 5 grams of salt per kilogram of fluid, you have such a big pressure drop between the reservoir and the well that those 5 grams are going to start to accumulate steadily at the point of production. And after only roughly a week, you're going to have like the well totally filled with salt. So basically then I just looked at, okay, what if we had then this enhanced bottom feed zone, and we also allow flow, from the above feed zones. Then what you see here is that because we allowed like much more flow from a very hot bottom feed zones, the whole well is much warmer, and so all of the fluid that is drawn in from the feed zones that are shallower will also encounter conditions that are very favorable for halite precipitation. Just because like this fluid coming from here are much warmer. So what's happening is that now, after about 3 weeks, I mean, this is a particular configuration. I don't remember exactly the permeabilities, but this is just to illustrate the fact that once you allow much more flow from the very bottom, the whole well becomes warmer, and you start to have like vapor plus halite. Like you reach the vapor plus halite field of the system inside the well, and so you have halite precipitating. And so, for instance, here you can see there's like roughly 80% halite, so the well has been almost totally filled with salt, and you have like a massive velocity increase, because like you have this constriction in the well. like the fluid coming from below suddenly needs to flow through a smaller cross-sectional area, so you have a big increase in velocity up to 100 meters per second, and this create again like a massive pressure jump, because like this velocity generates a lot of friction in the fluid. So this is like already at the edge of, I think, of the physics of the well. Like I'm not even really sure like this is capturing the proper physics of the well, because it's such high velocities. We don't really know what's going to happen to those salt crystals under those conditions. But basically what we can say is that if we allow a lot of flow from the bottom feed zones, then we're going to have a lot of halide precipitating in the well. So overall, I think basically what we come back to the normal case with all the feed zones having the right permeabilities and none of them being disabled or anything. And this is the odd case. So this is what we might expect in a few years from now, when once the formation has warmed back up to its initial configuration. And this is like actually the best we can expect, I think, with like a large inflow from this middle feed zone. And luckily just cold enough so that we have a little bit of liquid remaining in the well that can actually transport most of the salt out of the well. And so just quickly about the long-term trend. So this is not really IDDP2. This is another study I've made that I'm going to publish soon. But it's, I think this would probably capture the long-term trends of the IDDP2 well with the configuration shown in the previous slide. So here I just simulated production in different scenarios, but they are quite relevant to IDDP2 for 200 years. So a single producer. And like what Alina was, I observed the same trends as Alina's. So an increase in the mass flow rate over time because the fluid produced become denser as it's cooling down. You can see the temperature drop relatively fast. When it's fast, I don't know, because it's after 20 years, it's still only a drop of 20 degrees from 350 to 330 or so, and then start to stabilize at above or around 200 degrees in the next century. So, so what you have is, despite this, an increase in mass flow rate and an increase in the thermal energy produced by the well, because the increase in mass flow rate like overcompensate for the drop in enthalpy. So this is all like properties of at the wellhead of the well. So this is really what's coming out of the well at the surface. So yes, those 40 or so kilogram per second we see here, we might expect it to actually increase over time, and around 3 megajoules. So like here it's a bit less because there is again those the feed zone here that is decreasing the enthalpy of the well, but roughly maybe 3 or slightly less megajoule per kilogram will decrease, but not dramatically. I think what's more dramatic is the drop in temperature. Okay, so depending on what we really want, it might be fine, because we still have a lot of thermal energy produced. It's just at a lower temperature over time. So in conclusions, we managed to reproduce accurately the state of the formation around IDP2. And then we reproduce successfully the cold water injectivity test, so to calibrate the feed zone permeabilities. And we found that the well should almost naturally self-flow, and that most exchange will occur at 3,400 meters because of the presence of a highly permeable feed zone. But because of the previous cold water injection, the production will be delayed significantly, because we need to wait for the formation to warm back up, and this can take years. And again, another very important finding, I think, is that if the well gets too hot, there could be in saline formation. Again, it's very specific to this, there might be like massive halide scaling, and that could be very problematic, and it needs to be addressed, like how we design the well, taking that into account. So thank you.